Hi, in this video I'll be explaining about my project entitled Embedded Device for Phonocardiogram Data Acquisition and Classification. First, I will show you an animated demo on how the device works. The device consists of a stethoscope, a microphone, a Raspberry Pi with 4 buttons, and a speaker to output the results. When the user presses the record button, the device records the heartbeats of the patients through the stethoscope and condenser microphone to obtain a PCG. The user can then press the Diagnose button, in which the device will diagnose the recorded PCG as being healthy or abnormal. Two playback buttons are available for the user to replay the results of the recording and the diagnosis.
This figure shows the prototype that was created for the project. This device was created to make heart disease diagnosis accessible to all communities around the world through a simple-to-use device which can assist physicians in cardiovascular disease diagnosis. This project is motivated by the fact that cardiovascular diseases is the top cause of death in low to high income countries in all communities, where death is preventable by early detection of underlying cardiovascular diseases. Recorded heart sounds, also known as PCGs, are used to develop this device. Heart sounds are sounds produced from the vibrations of heart structures when blood is flowing through them. An abnormality of the heart sounds indicates abnormality within the heart structure itself. The PCG recording can be broken down into four segments: S1, systole, S2, and diastole, where S1 and S2 are the fundamental heart sounds. Now, to dive deeper into the development of this device, this is the system block diagram, which consists of heart sound acquisition, user control, pre-processing, feature extraction, classification, and output. When the PCG is recorded, it is corrupted with noise and sounds like this. To remove the noise profile is analyzed and removed using spectral gating, resulting in a denoise PCG. Next, Springer segmentation algorithm, which is a logistic regression and hidden semi-Markov model based heart sound segmentation algorithm, is used to segment the PCG recording. To do this, the homomorphic envelope, which extracts the low frequency peaks of the PCG, Hilbert envelope, which extracts the envelope of the analytical signal, power spectral density between 40 to 60 Hz, and wavelet features between 125 and 250 Hz components of the signal is extracted. In addition to that, the heart rate and systolic time interval is also extracted by taking the autocorrelation of the PCG to itself. The extracted features are then used to train the logistic regression model, which predicts the duration and probability distribution of the four states and is then decoded by the hidden semi-Markov model. The resulting segmented heart sound can then be used to extract more information in order for us to discriminate between healthy and abnormal recordings. A total of 151 features are extracted from the segmented PCG recordings, where the first 20 features are features that describe the relationship between the states and the state's duration to each other. Next, time domain features aim to describe the waveform and state features in time. Frequency domain features are described with the power of the signal, bandwidth, Q factor, and statistical information of the signals are also captured. Mel-frequency septal coefficients are fixtures used to represent the static and dynamic components of the power spectrum of the signal in a scale which mimics the human hearing range. Now that we have decided the features we want to extract from our segmented PCGs, what we need next is data, and the Physionet CINC 2016 dataset is used, which consists of 3,214 normal and pathological heart sound recordings from all around the world, which is recorded in clinical and non-clinical environments with different recording modalities. The dataset is imbalanced with 665 abnormal recordings and 2,575 normal recordings with an imbalance ratio of 3.74. And with this in mind, we split our dataset into training, validation, and test sets with a ratio of 67%, 16.5%, and 16.5%. The dataset is used to develop the machine learning classifier, in which 4 candidates were chosen for this project: an AdaBoost, GradientBoost, XGBoost, and an artificial neural network. Hyperparameter tuning using the random search optimization algorithm is used to tune the 4 classifiers on the training and validation sets to obtain the best hyperparameters for each classifier. In addition to that, post-classification thresholding is also used to tune the behavior of the classifier towards our desired performance, where we want to maximize our true positive rates. In the development of the classifiers, to distinguish between a good and bad performing classifier, the confusion matrix is used, where a good classifier will maximize the true positive and minimize false negatives, where the true positives are abnormal recordings classified as abnormal, and false negatives are normal recording classified as abnormal. After several iterations of training, validation, and classifier tuning, the best performing classifier was found to be the XGBoost classifier with a true positive rate of 86.61% and 91.79% true negative rate, and this is the classifier used in the final model. To conclude, a device capable of phonoelectrocardiogram acquisition and classification has been developed, and I hope that this video enlightened you on the development of such a device. The device has a 86.61% true positive rate when tested on unseen data in a test set, and the simple hardware makes it mobile, cheap, and easy to construct, thus making it accessible to communities in need. There are still improvements to be made on the device for better performance in the journey of dethroning cardiovascular disease as the #1 cause of death in the world. And that concludes my video on my project. Thank you.